Welcome everyone, and thank you for joining my talk. My name is Artur. I'm a compiler engineer at Azul where I work on Falcon compiler. In this session, we're going to be talking about escape analysis and related optimizations in Falcon. We'll start with brief introductions. I will tell you what Falcon is, I will define terms, what is escape, what is capture, and I will explain why we care. Then we'll look at the existing capture tracking analysis, and I will tell you what was missing there, so we had to build an analysis on our own. Then I will present Falcon's flow-sensitive escape analysis, and we'll look at a couple of applications of this analysis. In the end, we'll look at performance results, and I will conclude at that. Falcon is a just-in-time compiler for Java based on LLVM. We compile from Java bytecode into native code. We do this inside of a running JVM, and we execute the compiled code straight away. Falcon is the final tier compiler in Azul's Zing virtual machine. It means that we compile only a small fraction of all the methods being executed in the system, but these are the hottest methods, so the quality of optimization really matters for the overall performance of the system. This explains why we care so much about performance and optimizations in Falcon. Here are some links if you want to learn more. Escape analysis is a kind of pointer analysis to determine dynamic scope of pointers and objects. Specifically, it answers the question whether the given object or pointer is accessible outside of runtime scope of the current function or thread. And if we know this fact, this can enable various optimizations. Let's say if we have a lock object which is only accessible from one thread, we can eliminate any locking operations on this object because we know that there cannot be any contention. Escape analysis for Java is kind of a hot topic. This is because Java does not have value types other than built-in primitive types. So any record-like type will be heap allocated by default. As a result, idiomatic Java code will have a lot of short-lived allocations. They would often not escape the allocating thread, or with sufficiently aggressive inlining, they would not escape the allocating method. And this opens a lot of opportunities for optimizations. And typical optimizations you would expect to see in an optimizing compiler include optimization of storage for unescaped allocations. They can be scalar replaced, where every individual field is replaced with a scalar value as if there were no allocation to begin with. Or heap allocations can be replaced with stack allocations, because we know the runtime scope of the object. Another optimization you would expect to see is downgrade of thread-safe operations, things like lock elision or rewriting of atomic operations. Now, if we look at different transforms which use escape-related facts, we can see that they all need slightly different facts. For example, if we want to optimize a comparison between a newly allocated pointer and some other pointer, we need to make sure that the pointer to the newly allocated object cannot be inspected outside of the current function. Or if we want to optimize storage for an escaped allocation, we need to make sure that the content of the object cannot be inspected outside of the current function. Or let's say we want to do downgrade of atomic operations. In this case, we need to make sure that the content of the object cannot be inspected outside of the current thread. These properties are listed in the order from stronger to weaker. So if we know that the pointer value cannot be inspected outside of the function scope, we know that the pointer content cannot be inspected. And if we know that the content cannot be inspected outside of the function scope, we know it cannot be inspected outside of the current thread. So what often happens in practice, there will be an analysis to compute the strongest fact, and then different transforms would use the strongest fact and implication in order to assume the weaker facts they actually need. So from now on in this talk, I'm going to be talking about analyzing for the strongest fact, which is that the pointer value cannot be inspected outside of the function scope. And I will call this property no escape or no capture. Capture terminology is used in LLVM codebase. Escape is used in the context of Java. Because I'm talking about both here, I will intermingle those. Now let's look at what LLVM has in terms of capture or escape analysis. There is an existing analysis called capture tracking, and it answers the question whether the bits of the given pointer can be inspected outside of the function scope. And this framing makes a lot of sense for languages like C or C++, where you can take a primitive value and treat it as a pointer. So if we captured individual bits of the pointer, later we can construct a primitive containing these bits and we can treat it as a pointer. Implementation-wise, it's a fairly simple analysis. It looks at the uses of the pointer and essentially classifies them into three categories. There are uses which capture. Let's say we store the pointer into a global, and this global outleaves the runtime scope of the function. Or uses which don't capture. Let's say we pass a pointer into an argument, and the argument is marked as no capture. There are also uses which don't immediately capture, but the user would produce another value, which now we need to track in order to answer the question about the original pointer. And typical examples are instructions like gaps, bit casts, order space casts, things like that. And probably the main user of capture tracking in LLVM is basic alias analysis. So everybody who uses alias analysis either directly or indirectly through memory dependence analysis, memory SSA, would be using capture tracking facts. There's also a number of users which use it directly, and as I said before, often it is used as a conservative approximation of some weaker facts the transform requires. When we just started working on escape analysis optimizations in Falcon, we used capture tracking as the underlying analysis. But over time, we identified some limitations which in the end led to us building an analysis on our own. So let's see what we found. The first thing, and probably the biggest thing, is how capture tracking handles unescaped object graphs. Currently, capture tracking considers any store as capture, while in fact, if we store into unescaped memory, and this memory stays unescaped, the store is not a capture. It's funny, there is an unused parameter to capture tracking, store capture, and a more than 10-year-old to do, indicating, well, we can try to do something about this case. We can work around this limitation by iterative application of optimizations. Let's say if we scalarize leaf allocations first, the stores into these allocations will no longer be stores, they will be just SSA values. And after that, it will open other allocations, and they will become obviously no capture or no escape. But it doesn't work if there are cycles in unescaped object graphs. Let's say if we have doubly linked list kind of structure. And unfortunately, this kind of structures appear in the standard library for Java, and we need to handle these cases well. Another limitation we found is limited control flow sensitivity. Even if the allocation escapes at some point, we want to optimize the code before the escape. For example, there might be non-trivial amount of thread-safe initialization which we can optimize. Or the escape might only be on slow paths. In this case, we can and want to optimize the fast path. Capture tracking does have some control flow sensitivity. There is an optional parameter indicating the context in the function about which the query is made. And if this parameter is given, capture tracking would prune uses which are not relevant for the given context. And it uses dominator tree and is potentially reachable from in a conservative manner to do that. But it's not that hard to trick this part of the analysis. And lastly, there is an unexpected compile time impact. Capture tracking is a non-caching analysis. It means that on every query, it would scan through allocation uses. The main user of capture tracking, basic alias analysis, is also a non-caching analysis, so it doesn't help. So in order to mitigate potential compile time impact, there is an arbitrary cutoff on the maximum number of uses capture tracking scan through. And by default in upstream code, it is just 20. We've seen unescaped allocations with thousands of uses when we inline aggressively. So we want to handle these cases well, but we don't want to pay the compile time penalty. Now, after we looked at the limitations, let's look at the analysis we built in order to overcome these limitations. In short, this is a flow-sensitive analysis which models the points-to graph of unescaped objects by doing abstract interpretation. So it tracks some state, which is essentially the points-to graph. It traverses the control flow graph in the reverse post order, and it scans through instructions modeling their effects on the tracked state. The analysis and the corresponding transforms are implemented in downstream Falcon code. Potentially it can be upstream, but it will require some work because it uses some of the downstream concepts. But I don't think that there are fundamental things which would prevent that. So let's look at the state we need to track. Obviously, we need to track what have escaped, what not. And any allocation starts in an escaped state. When we see an escape, we simply forget about the allocation and stop tracking it. Also, we need to track all pointers to tracked allocations, including derived pointers. This is because these pointers can be used in order to modify or escape tracked allocations. Now, because we can handle the situation when a tracked pointer is stored into unescaped memory and we don't consider this as escape, we need to track the pointers stored into unescaped memory. Let me give you a couple of examples. Let's say we have allocation A and allocation B. We stored pointer to allocation B into the field of allocation A, and this store didn't escape immediately. But then, when we encounter an escape of allocation A, not only do we need to escape the allocation A, but we also need to escape everything A points to. Another example, when we see a load from unescaped object, we might be loading a tracked pointer to other tracked allocation, and we need to track it accordingly. For escape analysis reasons, we only need to track pointer fields. But our implementation of the analysis keeps track of every field of unescaped objects. This is because we have users of the analysis which require this information, and we will talk about this in details in a moment. So as I said before, we traverse the control flow graph in the reverse post order. This way, if there are no cycles, when we visit a block, we know that all the predecessors of this block will have already been visited and the out state of these blocks will be available. In this example, we start with the block in the middle. At the end of this block, we would have two unescaped allocations. Then we would visit the block on the right, and because this block has only one predecessor, we would just take the out state of the predecessor and continue analysis from that state. We would model the field modification and we would model the escape. Then we would do the same for the block on the left. Now, when we have a block which has more than one path coming into this block, we need to produce a state which would reflect the state of the analysis for all incoming paths. In order to do this, we take an intersection of all tracked allocations across all incoming paths. So if there is a path where some allocation escaped, this allocation would be considered escaped in the merge state as well. Then for every allocation into the intersection, we compute a set of tracked pointers, and this is a union of all incoming pointers, tracked pointers from all incoming states. And then we produce merge state for this allocation. So for every field, we produce a value describing the value of the field after the merge. So if all incoming paths have the same value as the field, we'll just use this value. But if there are different values coming from different paths, we need to create a phi value. And because we are doing a pure analysis at this point, we don't want to materialize phi nodes yet. So instead, we remember everything we would need in order to materialize a phi node if it is required, and we call this a virtual phi. So in this example, the merge state would contain one allocation, and the value of the field of this allocation will be a virtual phi. So it all works fine if there are no cycles in the control flow graph. But if there is a cycle, we would encounter a situation when I have a block for which the state of one of many predecessors is not available. In this case, we perform optimistic merge. We assume that the back-edge state does not affect the merge state, and we take the speculative state and continue analysis of the cycle. So once the back-edge state is available, we take the new back-edge state and reevaluate the merge. And if the new merge state is the same as our speculative state, it would say that we know the state of the analysis for the cycle. And if it's not, we take the new merge state and reevaluate the cycle. Because the tracked state is supposed to be a lattice, this iteration should eventually converge. So if we look back at the limitations of capture tracking, we can compare now. The analysis I presented is flow sensitive. It handles unescaped object graphs, including graphs with cycles, and it is a caching analysis. We compute analysis in one go, and after that we can make individual queries relatively cheaply. Now let's look at the transforms which can be made using this analysis. And I will start by saying that the analysis I presented maintains non-trivial amount of state. It maintains unescaped allocations with all of their fields. Currently, we do not support update to the analysis as the code is transformed. And usually it's hard to get this kind of things right. So instead, we do the following. We compute the analysis, then we collect a set of transforms we want to do. We discard the analysis, and then we apply the transforms. This way, we still need to care about update and invalidation, but only at the level of individual transforms. And because the transforms are very simple, things like remove this instruction, replace this value with that value, things like that, the update is also very simple. And usually it's just enough to wrap all the values into value handles. So all users of the escape analysis are currently organized as a single pass, which does various transforms. And we do everything you would expect to see from an optimizing compiler for Java. We do scalar replacement, and we do it as a series of transforms like store load forwarding, constant folding of comparisons, things like that. We do downgrade of thread-safe operations, we rewrite locks and atomics, and we do dead store elimination for unescaped objects. You may notice that we have ad hoc transforms for unescaped allocations here, things like store load forwarding, DSC, but yeah, LLVM already has these optimizations. The problem is the existing transforms don't have the escape analysis facts we just computed. And it's hard to feed this information into existing passes because in this case we need to solve the update and invalidation problem. So now let's look into a couple of examples in detail. We'll start with scalar replacement. If we have an escaped allocation, ideally we want to scalarize its fields and remove the allocation. And we do this by rewriting individual uses of the allocation in the way that they do not require the allocation value. So if we have a load from an escaped allocation, we can replace the load with the value we are loading because we keep track of all fields of the allocation. And yeah, this can be done by early CSC or GVN, but they don't have access to the facts we just computed. And what often happens in practice would have many of the cases handled by the existing passes by the time we execute our analysis. So we would only handle the hard cases here, which could not be handled by early CSC or GVN. We also do things like constant folding of comparisons, which involve unescaped pointers. Because we keep track of all possible pointers to unescaped allocations, we know whether two pointers can point to the same object or not. And again, there is an existing transform in simplify, but it doesn't have access to the escape analysis we computed. So are we done with this example? Well, not quite. There is one use in the deopt bundle, which prevents elimination of the allocation. Here I need to make a side note about deopt bundles and deoptimizations. Falcon uses speculative assumptions about the world in order to optimize the code. For example, we can constant fold a load from a global field, assuming that the field will never change. And we rely on runtime to check and invalidate these assumptions. And if any of the assumptions were invalidated, the compiled code is no longer correct and should be deoptimized. And if we were currently executing the code when invalidation happened, the execution should be resumed in the interpreter. So any call we have in compiled code may invalidate some of the speculative assumptions of the caller. And in this case, on return from the call, we cannot simply resume execution of compiled code. We need to jump to runtime and resume execution in the interpreter. So any call, in addition to normal return and unwind return, would have an implicit deoptimized return. So the deopt state in deopt bundle contains the values describing the abstract state to resume the execution from. It contains interpreter expression stack, locals, things like that. And these values are only used if deoptimization occurs. So they do not capture or escape, but these values, these uses, prevent elimination of the allocation. So in order to get rid of these values, of these uses, we make use of the fact that the allocation is unescaped at this point. So its identity have not yet been revealed. So instead of passing the value we allocated in the compiled code, we can allocate a new object So we would replace the allocation value with symbolic description on how to materialize the allocation value if the deopt occurs. And effectively, we are syncing the allocation and initialization code into Deoptimization path. And in order to do that, we need to know the state of the allocation, including all of its fields. So this is the user of the analysis, which requires information about all the fields. And after we do this rewrite, the allocation becomes removable because it only has initializing users. Now let's look at another example. This is escape analysis-driven loop unroll. Let's say we have a newly allocated, unescaped, linked list-like structure. And we have a classic while loop iterating over the structure. We're iterating until the current element is null. And if you look at this loop, it's not analyzable. We don't know the trip count. We don't know much about this loop. But the analysis we have effectively models the object graph we are iterating through. We can use this model in order to rewrite the loop and make it analyzable and possibly unroll it. So this is how the analysis would look like before the loop. And this is how the loop would look like in the LLVM IR. In our transform, we can recognize a loop candidate because we have a phi node which has unescaped object as an incoming value, and it has a dependent load on the back edge. We also have an exit which checks the current value for null. And because we know the structure we're iterating through, we can tell at which exact iteration number this exit would trigger. So we would rewrite the loop exit using the iteration count. So we would insert a canonical IV, we would rewrite the loop exit, and this rewrite makes the loop analyzable. In our example, the loop will also be unrolled after that. And after the unroll, store load forwarding kicks in, and the allocations become removable. Now let's look at performance implications of the optimizations I presented. Here I will be looking at comparison between the default configuration with everything I presented enabled and two crippled configurations. The first one has allocation state disabled, so we do not model the points to graph. At the same time, we still handle object graphs by iterative application of optimizations. And the other configuration is we disable flow-sensitive escape analysis paths altogether. We still have capture tracking and all the upstream passes, which can handle some of the cases, but we don't have the paths which I presented. If we look at a set of known benchmarks, which include SPAC, Da Capo, Renaissance, and some others, we can see that about 15% of all tests noticeably regressed. And this is about minus 3.6 geomean impact. And if we disable the escape analysis pass altogether, we have about 19% of the tests regress, and we have minus 16.4% geomean regression. There's also a number of tests which improve. I did not look into that, but I expect there is some unfortunate interaction with other transforms. If we look at a different set of benchmarks, which is a dedicated benchmarks for Java util stream API, and we know that this package is very sensitive to escape analysis. Actually, many of the cases, many of the transforms and analysis things I presented were motivated by the code in this package. We can see a dramatic impact here. So if we don't do allocation state tracking, we have 38% of the tests noticeably regress. And this is minus 19.5% geomean impact. If we disable escape analysis altogether, we have more than half of the tests regress and minus 32% geomean regression. And to summarize, Java code has a lot of opportunities for escape analysis. We started working on these opportunities, and we used capture tracking as the underlying analysis, but we identified some limitations. For example, it turned out to be very important for Java to handle unescaped object graphs. So later we implemented downstream analysis and transforms to solve these limitations. And as a result, we observed noticeable performance gains. But because we implemented it in downstream, now integration with existing passes is non-trivial, mainly due to update and invalidation problem. This is it from me. Now I'm ready to answer your questions.
Thank you, Artur. That was both a very interesting and also a very nicely presented talk. Well done. Let's go ahead and at this point dive into questions that are being asked by the audience. If you have any questions, please make sure to submit them through the app, or if you think that any of these questions should be asked early, please feel free to vote for them so they move up on our list of questions. Starting off with, Artur, are there any plans to upstream work that you've done here, either directly by upstreaming any of the code involved, or by using the lessons learned in upstream passes and analysis?
Yeah, that's an expected question. We don't have any immediate plans to start rolling patches tomorrow, but in the long term, we do want to upstream because generally we don't like to have lots of code downstream. And this is a pretty fair amount of code. Just to give some perspective, it's about 5,000 lines of code. Half of it is the analysis and half is the transform. And it will take some amount of work to slice it and generalize. As of technical challenges, I think the main challenge in the analysis part would be current implementation has some baked-in assumptions about the object model. So we use what we have in the VM to query information about object layout. We know some things like arrays have their length as one of the fields. This all can be generalized, but we would need to think of how do we express this kind of things in upstream, or whether we don't need to express it and we have some other way around this.
Okay. So next question is related to analysis and validation. In the talk, you mentioned that you had this sort of interesting scheme where you queued up all of the transformations and then validated them all, performed all the transformations at the end without sort of preserving the analysis. Do you think that there are lessons there for other analyses and transforms? And sort of what are the trade-offs of that approach over the more traditional keep the analysis up to date as we run transforms approach?
Yeah, overall, I would say that this was a useful trick, but it definitely has its own limitations. Specifically, we do not eliminate the problem of update and invalidation entirely. We just shift this from the analysis into the set of transforms. Let's say we have a transform which wants to write some instruction, but then we have another transform which changed it or removed. So we need to take care of this kind of interactions between individual transforms. And as long as the transforms are simple, we can get around by using value handles in most cases. And as long as we have a well-defined set of transforms and we can think of interactions between them, that works fairly well. And usually it's when we are doing this in the scope of one pass, we have full control over things we want to transform. But when transforms gets more complicated and the interactions between them get more complicated, let's say we want to run some transforms before some others, or the amount of information we need to keep for a transform is more than just a value handle for some instruction, that's where it gets tricky. And I would say that in the current development we are actually thinking of either splitting some of the transforms into separate passes so as not to solve this problem of interactions between different transforms where it's hard. Or as a general solution, we probably would like to move to more traditional update of the analysis, because we don't need to solve these problems of how does these transform interact between each other.
Okay. For next question, we're actually going slightly out of order because I saw a new one that popped up that looks interesting. So with the escape analysis that you're doing here, does this have any interaction with the garbage collector in terms of reducing the work for the GC by shifting objects onto the stack? And if it does, do you have any data or anything you can share on that?
So first, there is a transform which we could theoretically do by replacing heap allocation with stack allocation. We currently do not do that. We don't have it implemented. We do something very similar, which is scalar replacement, where we take individual fields and express them as scalars. So this way, it's up to the register allocator to put them where they need to be. But in general, yes, I would expect that this should reduce pressure on the GC. And assuming that what we have with scalar replacement is similar to stack allocation, you can look at the performance data presented and see the impact. And stack allocation has some nice properties which we cannot get with scalar replacement. For example, if we have some code paths where we merge unescaped object, pointer to unescaped object with some other pointer, currently we cannot scalar replace this. But if we did stack allocation, we would be able to have a pointer to this unescaped object. It would be a pointer into a stack, and we would be able to transform this code as well. So this is something we probably want to do at some time in the future.
Okay. So the next question is actually a question for me, which is doing this escape analysis, you're doing partial escape analysis. So meaning that you're doing transformations up to an escape that might happen. If you downgrade, say, an atomic store to a non-atomic operation just before a publishing store, what prevents the optimizer from, in a later transformation, reordering these two in a way that would expose the fact that the store is non-atomic to something that is actually potentially shared between threads now?
Yeah, this relates to a more general question. How do we make sure that when we publish a newly constructed object, the other thread observes fully constructed and consistent state of this object? And the answer to this question from Java memory model is if you want publication to be safe, you need to be using publication barrier in some form. So if the original program we are transforming does not have a publication barrier, it is a fair game for the optimizer to do this kind of transform. But if you want the publication to be safe, as a developer, you need to have the publication barrier.
Okay. So a new question just came in. Let me read this real fast. I can paraphrase. So it's talking specifically about accesses to hash maps. And if you have can you eliminate the allocation of a key? And as a result, can you actually combine two adjacent hash map accesses into one? I think that's what that's asking.
Yeah, this relies on inlining to happen because we currently don't do any escape analysis interprocedurally. So first we need to inline everything into one method scope. And after that, I think we should be able to do this, because after that we would have a new allocation for the key. We would have accesses to the key in order to compute hash code and compare it with the values in the hash map. So I think as long as if we can replace these operations in terms of the content of the created object, we should be able to do that. But I think it depends on how hash code and equals for the key is implemented.
Okay. Well, thank you very much, Artur. With that, we've managed to get through all of the questions everybody asked, and we're need to wrap up here in a moment anyways. Thank you very much for your time, for a wonderful talk, and a great Q&A. Thank you.
Thank you, everyone.